Okay, class 12. The topic of the day today is dielectrics. Okay, let's see. Dielectrics are basically insulators. All insulators, all dielectrics are insulators, remember. Alright, but keep in mind, all insulators are not dielectrics. Okay, it's like saying all alkalis are bases, but all bases are not alkalis. Okay, so remember, dielectrics are insulators. Now what is special about dielectrics is that in dielectrics dielectrics allow electric field to be set up in them when placed in an external electric field. So when you have an external electric field and you place a dielectric substance in there, what happens is, in dielectrics, okay, which are special kind of insulators, and they're special in the sense that dielectrics allow electric fields to be set up in them, okay, when of course they are placed in an external electric field. We'll talk more about this point. Okay, now some examples of dielectrics are mica, glass, air, oxygen gas, hydrogen gas, water, paraffin wax, carbon dioxide, etc. Okay, now first let us look at the types of dielectrics. Okay, dielectrics can be of two kinds. One is called a polar dielectric, and the other of course is non-polar dielectrics. So what are polar dielectrics? Polar dielectrics are those substances or are those dielectrics which have a net dipole moment of their own. They have a net dipole moment of their own. Now don't forget what an electric dipole is. Electric dipole, okay, I've already drawn over here, written over here. So two equal and opposite charges separated by a very small distance, which we have generally represented by 2L. Okay, this is called an electric dipole. Now any electric dipole has something called a dipole moment, which happens to be a vector quantity, of course. The direction of the dipole moment is from the negative charge to the positive charge. Okay, and the magnitude of the dipole moment is the product of any one of the charges and that of the separation between them, thereby giving us dipole moment to be 2ql. Remember that. So polar dielectrics, they have a net dipole moment of their own. Okay, now some examples of polar dielectrics are water, HCl, NaCl, ammonia, etc. Okay, now let us take for example HCl. So you have a positive ion H plus and a negative ion Cl minus. Okay, now the center of mass of the H plus is somewhere over here. Okay, and the center of mass of the negative charge Cl is over here. So what is happening is, the center of masses of these two ions, that of the positive charge and the negative charge, they are not the same. Okay, such that you have a net dipole moment, okay, directed of course from the negative charge to the positive charge. This point I've written over here. The center of masses of the positive and the negative charges do not coincide. This is one way of defining a polar dielectric. Remember, either you say this or you say this. Both are two different ways of saying the same thing. Another example, let us take water. Okay, so H2, this is H plus, okay, and oxygen minus, O minus over here. All right, now the center of mass of these two positive charges is somewhere over here, somewhere in between them. Okay, and the center of mass of the negative charge is over here, thereby the net dipole moment will be in this direction. All right, okay, so therefore HCl, H2O happens to be a polar dielectric. Same will be in case of NaCl and NH3 as well. But do remember, here when we look at H plus and Cl minus, likewise H2O, we are only looking at one molecule of HCl and one molecule of H2O. Okay, now when we look at water in general, say for example you have water in here. Okay, when we look at water, now this water is made up of a number of atoms, a number of molecules, let me rather say. Okay, now each of these molecules will give one dipole moment. Okay, each of the molecule constitutes one dipole, okay, giving rise to different dipole moments like this. Now what happens in case when we look at the substance on the whole is that individual dipole moments are directed in all possible directions. Okay, the individual dipole moments are directed in all possible directions. Therefore, when we look at the substance in general, the net dipole moment will be 0, because the individual dipole moments are aligned in all possible directions. Okay, so therefore the net dipole moment when we look at the substance on the whole is 0. Remember that. Okay, so this is about polar dielectrics. Now the other thing is non-polar dielectrics. Non-polar dielectrics, you can see the opposite. It's the opposite of polar dielectrics. So therefore, they do not have a net dipole moment of their own. They do not have a net dipole moment of their own. Like for example, H2, O2, CO2. Let us look at CO2 over here. This is the structure like for CO2. Okay, this positive ion C plus at the center, and you have a symmetrical O negative ions. Okay, thereby what happens is when you look at the center of mass of C plus, it's over here. Okay, and when we look at the center of mass of the two negative ions, okay, two negative charges, it is also centered over here. All right, exactly at the center. So therefore, the center of masses of the negative and the positive charges will be the same. Okay, so therefore you do not have a net dipole moment, or you can say you have one dipole moment aligned this way, you have another dipole moment over this way. Now since these are equal and opposite, so therefore they cancel each other out. Okay, so therefore non-polar dielectrics, they do not have a net dipole moment of their own, remember that. Okay, now this is what you need to remember about polar and non-polar dielectrics. Okay, now let us see what happens when we place a dielectric substance, be it a polar or a non-polar dielectric, irrespective of whether it is a polar or non-polar dielectric. Let us see what happens when we place a dielectric substance, dielectric material, in an electric field, in an external electric field. Okay, we are talking about this because we will be talking we have to talk about capacitors. In capacitors, what happens, like for example, say for example, this is a parallel plate capacitor. In between that, we've already spoken about a parallel plate air capacitor in the previous video. Okay, so these are positive charges on one of the plates and negative charges on the other plate. Okay, you have air in between the two plates. Nothing is inserted in between the two plates. We've already, this is what is a parallel plate air capacitor. We've spoken about this, and we've already calculated its capacitance. The capacitance was epsilon naught A by D, where epsilon naught is the permittivity of free space. Of course, there's free space. A is the area of the plates, and D is the separation between the two plates. Okay, now generally we don't have capacitor, we don't use air capacitors. What we use is we use capacitors which is filled, the two plates, the separation between the two plates is filled up by a dielectric substance. We will see what happens when we place a dielectric substance. Okay, so this is actually what we get. Okay, we have a dielectric substance placed in between the two plates. All right, okay, so so continuing with this, dielectric substance in between the two plates. Remember, so you have positive charges here, negative charges here, you have an electric field. So you already had an existing electric field. Now in this electric field we are placing a dielectric substance. So we want to see what happens when we place a dielectric material in an already existing or in an external electric field. Okay, so this is the case that we're discussing. So you have an external electric field, say for example E0, and you're placing a dielectric substance in there. Now this dielectric could be polar, could be non-polar, doesn't matter. Okay, if it is a polar dielectric, before so let me draw it over here. So this is the dielectric substance. If it is a polar dielectric, the individual dipole moments are aligned in all possible directions like this, whatever directions. Okay, now when you place it in an external electric field, what happens is all of these individual dipole moments, they get aligned in, let me draw it over here, all of the dipoles, they get aligned in a certain direction, individual dipoles. Okay, this is what happens in case of polar dielectrics. In case of non-polar dielectrics, what happens is, so this is the non-polar dielectric. Okay, doesn't have a net dipole moment, but it has atoms and molecules. Okay, so what happens is when you place it in an external electric field, the electrons or the negative charges, they get attracted to this side, and the positive charges, they get attracted to this side. Now why is that so? Because the electric field, the external electric field is in this direction, meaning it's like you have a positive charge over here, you have a negative charge over here. So the positive charge is attracting all of the negative charges, and the negative charge is attracting all of the positive charges. Okay, my pictures are very, very untidy. Okay, so let me move to a fresh page. Okay, so remember, basically what happens is, when you have a dielectric substance, irrespective of it being a polar or non-polar dielectric, okay, so when you place it in an external electric field, E naught is the external electric field, what basically happens is, if it is a polar dielectric, the individual dipole moments get aligned in this direction, in the direction of the electric field itself. Okay, and even if it is a non-polar dielectric, you have basically negative charges here and positive charges here. The same is true in case of polar dielectrics. Remember, the dipole moments gets aligned in this direction means you have negative charges here, positive charges over here, because dipole moments is directed in this direction from the negative charge to the positive charge. So this is the same thing is happening in case of polar dielectrics as well as in case of non-polar dielectrics. Remember that. Okay, so this is the case. This is the fresh picture. So basically, when we place a dielectric substance in an external electric field E naught, what we have is negative charges here, positive charges here, such that there is a new electric field which is generated inside the dielectric material itself. There is a new electric field which is generated in the dielectric substance itself, which is in a direction opposite to the direction of the external electric field, as you can see. That is called this electric field E dash. Okay, so E dash is the new electric field that is generated inside any dielectric substance when it is placed in an external electric field. And by the way, this separation of positive and negative charges that happens when a dielectric substance is placed in an external electric field, this phenomenon is what is called polarization. This is called polarization. So polarization means separation of, charges, positive and negative charges, okay, in an external electric field. This is what is called polarization, remember. Okay, so to polarize means to separate, to differentiate. All right, okay, not differentiate, to separate. Okay, so polarization. Now what else? Okay, yeah, so what we have is, we have an external electric field E naught and an internal electric field E dash that is generated inside the dielectric substance. So what happens is, due to this internal electric field that is generated inside a dielectric substance, okay, the net electric field decreases. Okay, the net electric field will be E naught minus E dash. Remember that. Okay, so the net electric field will be E naught minus E dash. Okay, and remember, E dash will always is a very small electric field that is generated compared to E naught. So E dash is always lesser than E naught. So the net electric field, when you place a dielectric substance in an external electric field, will be E naught minus E dash. So to say, the electric field, the magnitude of the electric field decreases, remember, when a dielectric is placed in an electric field. Okay, now this decrease in electric field is very much useful when we talk about capacitors. Okay, like I've already told you about a parallel plate capacitor, the space in between the two plates being filled up by a dielectric. So when this happens, when you fill up the space in between the two plates of a capacitor by a dielectric, okay, what happens is, the electric field in between the two plates decreases because of the presence of this dielectric substance inside the two plates. In between the two plates, the electric field decreases. Okay, so when the electric field decreases, the very first thing that happens is, when the electric field decreases, the potential difference between the plates decreases. The potential difference between the two plates decreases. Why? Because we know E is, the electric field is the gradient of the potential. I'm neglecting the negative sign for now. Okay, since E decreases, the potential difference between the two plates decreases. All right, now dr, mind you, is the distance. Okay, this, you can call this to be the distance between the two plates. All right, so when the electric field decreases, the distance between the two plates is not changing, but the potential difference between the two plates decreases. Now, when the potential difference between the two plates decreases, the very next thing that happens is, since we know C is Q by V, where V is the potential difference between the two plates, when V is decreasing, the capacitance of the capacitor increases. Okay, so this is why we use, so capacitor basically is a device which is used to store charges. As you know, more and more charges it can store, the better a capacitor it is. So therefore, in order to increase the capacity or the capacitance of capacitor, all right, we place a dielectric substance in between the two plates of the capacitor, because of which the electric field decreases, the potential difference between the two plates decreases, thereby the capacitance of the capacitor increases. Okay, we are going to talk about, we are going to speak more on this, all right, in the next video. Okay, for now, I think this much will do. Okay, so thank you.